Okay, now that we've set the definition for what rapid drawdown is, let's look closely at how we would go about analyzing that. This technique is often called a multi-stage analysis, or in some cases it's called a three-stage method. So the three-stage method, for many years there was what was called a two-stage method, and then Duncan, Wright, and Wong published an article and developed what they call a three-stage method, and it seems to be the preferred or standard method now. So what are the three stages? Stage number one, compute effective stresses based on pre-drawdown conditions. And so you take the dam or levee at a full pool stage, you run a seepage analysis using something like Seep2D, and you use that to get the pore pressures along the failure surface. From those pore pressures you calculate effective stresses, and those are calculated all along the base of each slice along the failure surface. Then using that, you compute the factor of safety of post-drawdown conditions using a total stress analysis. And so you use the geometry of the slope is such that the water is lowered, the soil is fully saturated, it's still heavy, you don't have the buoyancy effect. Furthermore, the undrained strengths you use along each slice of the failure surface are dependent on or a function of the confining stress. So basically, undrained strengths are still a function of the effective stress during the consolidation stage. And so that's why we use the effective stress at the consolidation stage. In this case, is the pre-drawdown or full pool conditions. Full pool. And so, yeah, then we use those undrained strengths derived based on the effective stress at pre-drawdown conditions, and then we do, in step two, we do a slope stability analysis using those undrained strengths and the condition with the water lowered in the heavy soils. We calculate a factor of safety. Then what's different about this method compared to the two-stage method is then you go back and you calculate the factor of safety for post-drawdown conditions using drain strengths. And then in some cases, it doesn't happen too often, but in some cases that factor of safety from drain strengths ends up being smaller. And so you effectively just use the lower of the two, the factor of safety from stage 2 or stage 3. Okay, so now we're going to dive into how the calculations are done, but this is the most critical thing to understand in terms of a multi-stage analysis. All right, let's look at it in a little more detail. Again, stage 1, we do this for conditions prior to drawdown, and so we take this phreatic surface here. Again, the best way to do this is with seepage analysis, but even if you don't have a seepage analysis, you can calculate the pore pressure based on the distance. Take the bottom of each slice, calculate the distance below the water table, and use that to calculate pore pressures. Either way, you can get pore pressures along that candidate slip surface and then use that to calculate the effective stresses. So this is a pretty simple part of the process. And again, we're calculating the effective stress along the bottom of each slice. This is the free body diagram we had earlier. We have the normal force N. So sigma prime FC means the normal force on the failure plane at the end of the consolidation stage. And that is equal to the normal, the normal stress, the effective normal stress on the failure plane at the end of the consolidation stage is the normal force at that point divided by delta L minus the pore pressure. So this is how we calculate that effective stress. Now, the shear stress along the failure plane at the end of consolidation stage, well, it's the mobilized shear strength, or this shear force here divided by delta L. But this sigma prime FC, the effective normal stress on the failure plane at the end of the consolidation stage, is what we're going to use to figure out what undrained strength to use. And again, we assume steady state seepage if we're doing a seepage analysis. And as I mentioned before, the effective stress sigma FC, that should be a prime on there. Sigma prime FC represents stress along the failure plane at the end of consolidation stage. And this is what we use to calculate the undrained strength in stage 2. So here we are on stage 2. Now the water table, or the pool, has been lowered. The undrained shear strengths and total stress analysis is used for the low K zones. The undrained strengths are estimated using the consolidation stresses computed in stage 1, as we've discussed, and the driving forces are calculated using post-drawdown conditions. And so this soil is still wet and saturated. You have the weight of that going down. I mean, this diagram shows this phreatic surface here, but in reality it's going to be up here somewhere, because the whole point is it hasn't had time to fully consolidate. All right, now how do we go about taking those effective stresses at the end of the stage 1, the consolidation stage, the pre-drawdown stage, and using that to compute the undrained strength on the failure plane at the base of each slice? So if you look at the failure plane, the Mohr circle at failure, and we look at it in terms of effective stresses, this is the sigma 1 and sigma 3 at failure, so the major and minor principal stress at failure. It's tangent to the failure envelope. Tau FF, this is the shear stress on the failure plane at failure. And using sigma 1 and sigma 3, we can use this equation up here to calculate tau FF, the sigma prime on the failure plane at failure. Now, if we know for this particular test what the normal stress is on the failure plane at the end of the consolidation stage, sigma FC, should be sigma prime FC, then if we pair sigma, this shear stress on the failure plane at failure, which is basically the shear strength, tau FF, if we combine that with sigma prime FC, the normal stress on the failure plane at the end of the consolidation stage, we can come up with a new plot, which is tau FF versus sigma prime FC. Now, there are multiple versions of this, depending on this thing K, which we'll talk about in a minute. But let's assume we're looking at this line here. Then this sigma prime FC, we get that from stage 1. This is the effective normal stress on the failure plane at the end of consolidation stage. And then we can just come up here and scale off the corresponding shear strength on the failure plane at failure. And then we can plug that right into our analysis and calculate the factor of safety at stage 2. Now, however, there are multiple curves here depending on what the K factor is, the shear stress ratio is, excuse me, the normal stress ratio is during the consolidation stage. So this K is equal to sigma 1 over sigma 3. And when K is equal to 1, that means sigma 1 is equal to sigma 3. And sometimes when we do an undrained triaxial strength test, during the consolidation stage, we let K1 equal to K3. But then, as you apply a deviator stress and sigma 1 becomes greater than sigma 3, eventually you reach failure. And that gives you the KF term. KF is the ratio of these two stresses at failure. Now, it could be that when you consolidate, you're right on the verge of failure. So KC equals KF. This upper line means the shear, the normal stress ratio here during the consolidation stage is right at the verge of failure, and that is KC equals KF. So in reality, the K value during the consolidation stage has to be somewhere between these two extremes. It can't be lower than this, and it cannot be greater than this. So it has to be somewhere in here. And in a couple slides, I'll show you how we can calculate where we are in here, depending on what this ratio is during the consolidation stage. Now, how do you go about getting this? It's actually not hard to get. The KC equals KF line for a CU triaxial envelope is the same as the one obtained from a CD or CU bar triaxial drain test. So this is basically when you do a CU bar or a CD test, for example, you slowly increase sigma 1 and allow it to come to equilibrium very slowly until it fails. So basically, KC equals KF for a CD test at failure. Or if you do a CU bar test and pull out the pore pressures, you can get the same effective stress C prime and phi prime. And then the KC equals 1 line represents what you would get from a CU test, where you have sigma 1 equal to sigma 3 during the consolidation stage. So in other words, if you do a CU bar test, you can get both of these lines. Okay. Now, the trick then is we need to find, using sigma 1 and sigma 3 at the base of each slice, we can calculate sigma 1 and sigma 3 and come up with a KC value, the ratio during consolidation, and it's going to be somewhere between these. For example, let's assume KC is equal to 2 and KF is greater than that. Somewhere in the middle here, that's going to be the curve that we want to use. And so what we do then is we calculate KC, and then we interpolate. It's going to be between 1 and KF, and we find where we are in this spot. So now we're going to call this term K. Whatever our K value is at the end of the consolidation stage, we're going to call that K1, the K from stage 1. All right, how do we get K1? Well, it turns out there's a simple equation we can use. We use the phi prime we get from our drain strength test or CU bar test, and we calculate if we have the effective stress and the shear stress, we can plug into this equation and we can get K1. So sigma prime and tau are the effective normal and shear stresses on the shear plane at the end of consolidation. So this would be on the base of the slice. So we get that. We go back. This comes from this free body diagram here, and we just plug that in, and we have K1. So that tells us where, again, we're going to use that to interpolate here. But how do we get KF? It turns out if you have no cohesion, it's just tan squared 45 plus phi over 2. But if we have cohesion, we use this bottom term. And so now we have a way to get K1, we can get Kf, and so now we use this equation to interpolate those curves. And so Kf minus K1 times tau F Kc equals 1. That's the bottom curve. K1 minus 1 tau Ff Kc equals Kf. And then we plug in K1 and Kf, which we found on the previous slide. So again, so this is the, so for a given normal stress, we come up here and we get a tau Ff Kc equals 1. We get a tau Ff at Kc equals Kf. And we plug in the values for K1 and Kf that we found, and we can basically linearly interpolate between these. So that's what, so this expression right here is how we interpolate those two curves. Now, it sounds complicated, but it's a pretty simple calculation once you get all these terms set up. And then another thing we do, if significant cohesion exists, then the sigma 3 prime values can become negative. In other words, your Moore's circle can be like this. Sigma 1 will be positive, sigma 3 would be negative. And we don't ever want to count on negative normal stresses. And so basically, to be conservative, once we get down to here where these lines cross, we're just going to use the lower of the two so that we don't rely on negative pore pressures. And so we just use these two equations to check for that. For the Kc equals 1 envelope, we calculate sigma prime 3 this way. For the Kc equals Kf envelope, we calculate it this way. If either one of these is negative, no interpolation is required, and we simply use the lower of the two strains coming from the two curves. Okay, so that gives us our shear strength on the failure plane. And again, it's a function of the effective normal stress on the failure plane from stage 1. That gives us the shear strength we're going to use for phase 2, for stage 2. And so then we go ahead and once we have these undrained strengths, we calculate the factor of safety. If you have a high K zone, like a sandy shell, you'd use drain strengths. And that for the low permeability soils, use the undrained strengths. And then our driving forces, based on the weight of the slices, are calculated using post-drawdown conditions, so no buoyancy effect. All right, so that gives us the factor of safety of stage 2. Then we proceed to stage 3. In this case, we use undrained strengths for slices in low K zones, and we compare those to the drain strengths. And if the drain strength is lower than the undrained strength, then the drain strength is assigned to that slice and the factor of safety is recalculated. So some slices you may be using drain strengths and others you may be using undrained, whichever is most conservative. And if the drained is greater than undrained for all the slices, and then clearly the stage 2 factor of safety is the critical one. And for the drain strength calculations, we just plug in using our drain strength parameters, and the pore pressure U is found from post-drawdown conditions, so pretty simple, straightforward. And if stage 3 calculations are required, in other words, the drain strength is less than the undrained strength in at least one of the slices, then the stage 3 factor of safety becomes more critical. If it's not required, then we use the factor of safety from stage 2. So that's it. That is how we calculate the factor of safety for rapid drawdown analysis using the 3-stage approach.